Okay, so last week we discussed the unperturbed universe, homogeneous isotropic treatment universes with FRW metric. And yesterday we discussed the first stuff in perturbation, which was the cosmic quark wave background, and we found peaks, which were sound waves at first compression, first rarefaction, second compression, and so on, that the location of the first peak was well described by a zero-order approximation of photon fluid with a sound wave because it has pressure P third row, C squared, if you want. And so you can do a continuity equation, Euler, and so on, and linearize and get a wave equation. You found a sound speed, and you could know the curvature of the universe from there because things appeared further away for the same co-moving distance if it's negatively curved like that. Those are integrated subs-wood. You could also test dark energy models, lambda and other dark energy. When you had baryons, you had loading, so the rarefaction was smaller. And if you had the dark matter, the third peak, the second compression was larger because the second compression goes away if you don't have potential wells that are deep enough. And so the ratio of these two things is really a ratio of baryons to dark matter. So from there you could deduce the universe parameters and get a Hubble constant because the angular diameter distance to the CMB depends on Hubble constant. So you can get a Hubble constant that is a bit low compared to local values, but really, you know, it's just the precision is so large that it's 4 or 5 sigma. But in pure numbers, it's not that different. 68 and 73 kilometers per second megaparsec. We did all that by doing Fourier analysis on spheres on multipoles so that we could get angles instead of wave numbers, instead of wavelength. And when we did this Fourier analysis on multipoles, we found different scales, which correspond to different angles. These are different scales. Okay. Well, this is from Wayne pages, as I mentioned. Okay, so, but this coupling of the baryon photon fluid until 400,000 years means that they can't start to collapse. The baryons have a sound speed more or less equal to the photon speed, which is more or less equal to the speed of light. It's 1 over square root 3 the speed of light. So they can't, the Jeans length, which we'll get to again, we did it last time, but we'll get to again. Before recombination for the baryon is huge. It's the size of the horizon, so they don't cluster. Okay? And then there's damping, the silk damping here, diffusion damping because of the diffusion, that destroys the initial perturbations if they existed. Well, they did exist, but we can fit them here very well with the lambda CDM model. These are data and this is the model. As you can see, it's quite not bad at all. But they damp in the baryon photon fluid because of diffusion damping, especially near recombination when plasma turns into atoms, mainly hydrogen atoms with some helium and traces of lithium, beryllium, and whatever. Okay? Deuterium, and so on. So therefore you cannot form galaxies because at the scales of galaxies, everything is damped. Galaxies are somewhere here where everything is damped in this scale. In fact, the last thing you can see is 10 megaparsec and a galaxy starts at a kiloparsec. So it's 10,000 times or so. Right, so we need dark matter for all these reasons I mentioned from the CMB. In addition to rotation curves and dynamics of galaxies and clusters and so on, virial theorem and all that, you need dark matter. And if it was in thermal equilibrium in the early universe when it was really hot, then it needs to have small velocity so that it can cluster, and that means relatively high mass. So in the standard what they call weakly interacting mass of particle paradigm, it's sort of 100 GeV. The minimum you can have if it's thermal is like in the keV scale. Okay? 2, 3 keV. And that's called warm dark matter. The other is called cold dark matter. Okay, so we're back to square one, our Euler equations here. This is Newton's law written in the Lagrangian derivative following the motion of a fluid particle. A fluid particle is a box containing many molecules, if it's a gas, say, or many photons, if it's a photon gas, and small compared to the size of the whole system. And things in this approximation don't diffuse. So we only have pressure, the isotropic terms of the stress tensor, of the 3x3 stress tensor. We don't have viscosity and damping and so on, which are anisotropic terms, shearing and things like that. And these are the forces. So this is Newton's law written for a fluid, and Poissons equation, and we got this equation when we added the Poissons equation of gravity, and you can solve it because this is by linearizing, meaning small perturbations. We got sound waves that turned into collapse at the gene scale when this became negative, because then the solutions are not sinusoidal, cosines and sines, they are exponential, e to the power t. Omega t. And omega is not a frequency anymore, but a blow-off characteristic scale. Okay? And this is called the gene scale. What's a gene scale? It's time that the sound crosses the system compared to the time that the system collapses, called the dynamical time. This thing here, 1 over square root 0, is called the dynamical time, the time that the system collapses. The gene scale is when the sound, let's say horizon in your system, but that can be a galaxy, it doesn't need to be in the universe, the time sound takes to communicate the pressure is longer than the time of collapse. So things collapse. The pressure cannot prevent things from collapsing. Okay? So that's the gene scale. So we asked in the very first lecture, or thereabout, or last lecture, can galaxies form then through genes collapse of baryonic matter? No, they can't. At least not in our standard picture, because of the things that I mentioned about the CMB, for example, and silky damping and all that stuff. Okay, so they can't. You need dark matter, and you need it to be massive. There's something wrong with this thing, but that's the point. In thermal equilibrium, mv squared is k Boltzmann t, and that's a classical equipartition. Okay. And the dark matter is classical at the stages meaning non-relativistic and non-quantum at the stages we are looking at. So therefore, you need to be massive so that it's temperature adaptive. This is what it says. And it's not coupled to the baryon photon bath, so it can start collapsing earlier, and it's not damped, and everything it decouples from this black body radiation of the thermal equilibrium of the photon baryon flow. It just decouples because it's weakly interacting. Its interaction timescales are not long enough, are not short enough to keep up with the expansion. So it's simply after some time, a dark matter particle does not meet another dark matter particle ever in the history of the universe, and does not meet any baryons or anything else, actually. Okay? Anything that's weakly interacting. And it's not electromagnetic, otherwise we could see it. It's not strongly interactive, otherwise it would make nuclear fusion, and we'd see it probably, and so on. Need to describe this dark matter seeds now. In order to do their job, it needs to be non-relativistic early on, because if it's relativistic, it will have a sound horizon of the speed of light. It will have, it cannot cluster, okay, because its gene scale is of order of the speed of light. Okay, gene scale is the order of the time, the Hubble expansion time times the speed of light. Okay, so it's very long. So order of the horizon. The Hubble sphere. We also assume that the scalar small here in our definition compared to that Hubble sphere, which is C h minus 1. Now it's h is the Hubble parameter, a function of time, so not Hubble constant. Before we defined the Hubble sphere as of now, but this is more generalized. This is as in the Newtonian derivation of the Friedman equations, when we said the communication time is smaller than the expansion time. We're going to do this again here and mention GR connections when relevant, when absolutely necessary. Take into account expansion, but we need to take into account expansion. These things here, this equation for the fluid, this is all for a laboratory fluid that's not expanded. We need to expand it, so we need to put coordinates like that. These are called co-moving coordinates. Let's say we take A equals 1 today, then R equals X, and these are co-moving coordinates. We did co-moving distance before, where everything was measured, the distances were measured in today's scales. This is basically coordinates measured in today's scales, so therefore, by definition, they're invariant. So, the moving coordinates of the particles in a Hubble flow are A of t times x. And if there is no what we call peculiar velocity, we simply have the Hubble flow. Okay? Locally speaking, this is local, huh? Okay, yeah. So we simply have the Hubble flow. The velocity of galaxies proportional to their h of t for fixed t. And we have this peculiar velocity in addition. This comes just from differentiating. Right? Then the derivatives, as you may expect, the nabla, the gradients, with respect to the co-moving coordinates, have a scale factor, with respect to the physical coordinates, the one that actually do. If last week, that's what we dealt with. We dealt with homogeneous isotropic and expansion. Now we're considering some speeds with respect to that. That galaxies can have some speeds with respect to the Hubble flow, with respect to the expansion. Okay. The physical time derivative is now like the total Lagrangian derivative before, following the motion of the particle. So it's a total derivative that's written like that in terms of the co-moving case today. Okay? So it's written like that. Then you can do a second derivative. Now, mind you, this is tricky if you're in Newtonian, because you're going to have to ignore terms with the h-dot acceleration, because these communicate between different FRW times, back and forth. And that's not allowed in Newtonian. This is a local frame. So you can think about it. It's like a free-falling frame, or a free-falling frame. A bit more formally speaking, if you divide these by that, for example, or that, you'll find that these are scales of the local motion inside our radius r, which we consider small compared to the Hubble radius, compared to the Hubble horizon. Not necessarily particle horizon, the Hubble horizon, but I hope we'll get to that. The time of crossing of these small scales that we are studying compared to the Hubble time. Divide that by that, you get h minus 1, and you get r over v, which is the crossing time for our local things going on with their peculiar velocity detaching from the Hubble flow. And we are interested in things, by definition, that are forming on scales much more smaller than the Hubble time, which is, for normal matter, the age of the universe, more or less. So or the age of expansion, if you want. Okay? So we want things that are moving on short time scales compared to what the universe is moving, the different time slices of proper time. Okay? So they don't communicate through that in the Newtonian thing and this local. So this is okay once you're local, and it's like a free-falling frame. Otherwise, you need your covariant transformations and so on between the different frames, and there'll be extra terms in the GR. Here, there aren't. There are local frame free-falling, and there are some extra forces physical. So, when you have these extra forces zero, an interesting thing is that the peculiar velocities always go towards the Hubble flow. They go as 1 over A. As A expands, these go as they decrease. This is like redshifting for photons, but it's for matter that is not massless. Okay? It's for particles that are not massless. The photons redshift, these particles decrease their velocities with respect to the Hubble flow. And that means also that if particles were relativistic but we have mass. Sooner or later, with the Hubble expansion, will become non-relativistic. And this is an interesting thing in the early universe. Particles become non-relativistic. So the dark matter and baryons and everything almost was relativistic. But at some stage, when the temperature in natural units was equal to its mass, and then decreased less than its mass, they became non-relativistic. That's mass. So let's write a density contrast, rho minus rho average for the universe, and we'll have now a little perturbation, a linear perturbation over rho average, and you can write your rho like that with delta small, and you can write your Poissons equation like that. It's Newtonian. We'll get to how this can, in some cases, still work in general. And then you can have a zero-order continuity equation. This is obvious from there. Okay, so this is like getting your initial continuity equation, and which is rho dot lambda r dot rho u. Rho is not dependent in the background on r because it's homogeneous isotropic, and lambda dot u is just simply lambda dot r, which is 3, and the Hubble constant. And this is 0 because it's in the background. This is obvious. This is a bit less obvious. You can try your luck out doing it. If you can't, there's how you do it is there in some textbooks, like and papers and review papers, school papers like Peacock, large-scale structure, and so on, and the book by also Mo van den Bosch. Mo van den Bosch and White. Okay, so but this is very interesting. So try to do it. This is the perturbed continuity equation for delta because it relates the growth of these perturbations with time in an expanding universe with these velocities in the co-moving coordinates, with the gradients of these velocities. And you can measure these through something called the redshift distortions. Looking at the redshift of galaxies and saying things that are sometimes called the fingers of God, because they in the redshift they seem like lines where the things are custom. They distort the redshift, which is homogeneous. In homogeneous isotropic, it looks all homogeneous isotropic on spheres, on surfaces. But then you have these peculiar motions which have fingers. And from that, you can make measures of the growth factor and the growth rate and then growth factor, which is very important to measure how things grow because these depend on dark energy sensitively. And this is one of the missions of Euclid, for example, which was launched a couple of 3 weeks ago or something. Okay, so this is quite important. Try to do it. The other very important equation is transforming this one, which we did before, the sound waves with the gene scale and so on, to this one. This is also very straightforward. You just divide by the rho average, which we call our rho naught. Okay? For simplicity of power. And then you put your scale factor again. You want expanding, you transform it like that. The new thing is there is a Hubble constant, a Hubble parameter here in this thing. Okay? And there is a scale factor. Otherwise, it's like this. This is expanding, this is non-expanding. This is the second order differential equation for the growth of the perturbation. I start with a small perturbation. I want to know how does it grow or doesn't grow or whatever it does. I want to know because that's where I'm going to form galaxies from, halos of galaxies. This is dark matter. Well, this can be baryons also. It's still not the dark matter because this has this guy. So what do we do here? Also, there's the k-square. This stuff I talked to you about. You should know it by now. This is nabla squared over IKR is just minus k squared IKR. So I can Fourier transform my equation here and get this, and then divide by rho. Okay, so this is quite simple. This is a bit more complicated, but again, you can go and look at the textbooks to derive it if you can't do it on your own. Now, notice that before we had Fourier series in K and omega. We don't have omega anymore. We can't do omega. We can't do this trick here in omega anymore because we have this guy in time. we have the expansion. So we're not homogeneous in time like before. So we can't do the trick of the IKR. And therefore, any growth will not be exponential like before, because we can't do the Fourier analysis in time. We can only do it in space. Yeah. So, you noticed with the temperatures last time, this term doesn't exist for the photons. It's because this is redshifting of light, of particles. The velocity changes. The other one is redshifting in photons. There's no velocity change, so you don't get that. It's built in the redshift. So let's do dark matter like we said. Almost zero sound speed, doesn't have any pressure, it decoupled long ago, it's very heavy, mv squared is equal to kt, and m is very large, and so on. So that means that we take this term out. Things with zero sound speed, they collapse on the dynamic in time, except for the expansion, and except for something else that we'll see now. So things with zero sound speed are described in the matter limit, small scales, non-relativistic from special relativity point of view, and from general relativity, they communicate very fast together and so on. From the point of view of relativity both, looks like that. Okay? So the gene scale is really zero here. Anything collapses. Well, there is a small free streaming length we'll get to, but that's not important for what we're talking about. Everything collapses, and this is really scale-free. Okay? There's no scales in this one. So let's try solutions in the matter-dominated flat Einstein de Sitter universe, which is a flat universe that we did in the first week with h squared equal a dot over a squared Friedmann equation, proportional to rho naught, the background density. Remember, the rho naught was like 1 over a cubed, because simply expansion of non-relativistic matter, volume goes down as the volume, scale factor, and that this was proportional to 2 over 3. A was proportional to t over 2 over 3, so you get t squared here. Put this t squared here, and put this 1 over t squared here, and try to solve this equation, you get t to the 2 over 3. What does that mean? It means that the perturbations grow with time as the scale factor, because the scale factor also grows in these universes, like we did first week, as t 2 over 3. So this grows from a matter-dominated universe as t2 over 3. Okay, grows on the scale factor. That's why we couldn't, even without this thing, we cannot do the omega, because it grows. We cannot do the trick with omega. We can only do it with k, because it doesn't blow up exponentially. The expansion made it grow slower. Okay? So, non-expanding fluid without any pressure, gravity makes it collapse exponential with time, e to the t. On a time scale 1 over square root 0 initial density. Expanding universe is proportional to 2 over 3, not exponential, slower because of the expansion. Now what happens, and this is proportional to conformal time squared, when you need it maybe later. Okay? You do the integral, dt over a of t, and you get that. For the radiation, and it's also for radiation, but for the matter. Okay? So, but what happens if you make this expand much faster than the collapse time? This will happen if the universe is radiation dominated in the beginning. As we said more than once, in the beginning, 1 over a to the 4 for radiation energy density goes down, 1 over the a to the 4, because the number density goes down, and the temperature or the energy of each photon also goes down as 1 over a, redshift. So it's 1 over a to the 4. Okay, so in the early universe, after inflation and so on, the universe was matter with the radiation dominated until the radiation going down as 1a to the 4 becomes less than the matter going down as 1a cubed. They always increasing with time, at least in these universes we're talking. Right, so what happens if a radiation dominated here? This dominated means the H will be large due to the radiation, and rho naught due to the matter here will be small. So I get something called the Mazaros effect. The matter can't grow. And you can do this formally by putting rho naught going to 0 in here, and this much larger than that, and you get delta going of matter, delta of the matter going as log time, which is much slower than this. Log is much slower than power law by 2 over 3. Yeah? So this is called the Mazaros effect. This is important for the power spectrum that we'll speak about. So heuristically speaking, we can understand it like that. The expansion time for a flat universe is 1 over square root g radiation when it's radiation dominated. This is the expansion. This defines the expansion time. Okay, it's reversed defines the expansion time. And this is proportional to rho naught. So I put rho naught radiation, background radiation. This will be smaller than the collapse time, which is 0 matter, the dynamical time of the collapse. So the universe is expanding in the radiation era much faster than, and it's the same, by the way, in a cosmological constant, inshallah. Nothing will collapse anymore. But in a radiation-dominated universe is expanding much faster than the matter can collapse, so matter cannot collapse. It collapses very logarithmic. Okay? Now, this is important, we said, for finding power spectra. What are power spectra? Find them. Power spectra, we kept on doing this informally all along, expanding things in Fourier series and taking modes and so on. This is not, this is tricky. Okay? The formal thing is that you write a Fourier transform, Fourier integral, okay, and say that your delta of R field of fluctuations, meaning delta everywhere, how far does it go away the density contrast on the average at some radius vector R, can be expanded in infinite, continuously infinite Fourier modes. And these things here define, complex numbers on a complex plane. These are phases, theta, and these are amplitudes. Okay? So the squares of the amplitudes is the power spectrum. And you take this and its conjugate, so the e to the power IPR go, and you square it. The volume here is a convention, but I put it because you can take it off. It all works out in the end when you do the inverse transform and so on. And the power spectrum is independent. For example, this convention, this goes down as 1 over b, so but this convention is nice also because these are dimensions. And the power spectrum is dimensional. It has a volume. Right? So the power spectrum is basically, formally speaking, it's also an average over many realizations of your universe. Okay? Many different random realizations for a random field. We'll get to a bit about random field. Okay? I don't know, this watch is not working very well, so its time scale of error is long, so it's okay. It didn't make much error. It made in the morning. Okay, so right. So this is the absolute value, the radius of your complex number, square. There's also an important quantity called the dimensionless power spectrum. This is dimensional volume. This is without dimension because it's multiplied by wave number cubed, which is 1 over lambda cubed. So it makes us dimensional. That's another reason I wrote this volume, because to get you an intuitive feel of what we're talking about. Okay? So this is dimensionless power spectrum. It measures the variance per logarithmic interval. If we're talking about a random field here, this is not necessarily random. This can be, by the way, a function, expansion of function of Fourier modes. But if it's not random, at least, then you will need to know the phases also to get a complete description. And you need boundary conditions for that. If you want to know more about that, we can talk later. Because that's how you solve a Poissons equation, numerically read, by fast Fourier transform, but with a boundary condition for a galaxy. But that's another story. That's not what we here assume no boundary. Okay? So, right. So this is dimensions power spectrum. This is the variance. What is the variance? You know from statistics what is the variance of a random number, of a random variance of a statistical distribution? You know?
Difference from the mean.
Okay, it's the difference from the mean squared, the whole average. Okay? So the whole variance for this field is, because these are delta k's, so you integrate, and because of 3 dimension, you integrate over 3-dimensional volume in k, of p of k. You integrate the fluctuation squared over k's. For all k's, you get the total variance. Right? Delta k squared, I integrate it over all k, I get the total variance. Okay? This is the variance per unit interval in k, in the Fourier picture. Okay? And it's equal to that. This guy times integrated over d logarithmic intervals of k. Meaning, this guy gives you per octave, for logarithmic, in the relative fluctuation, the variance, per unit log k, meaning from 0.01 to 0.1, from 0.1 to 1, and so on, in octaves. Okay? So this gives you the relative fluctuations at the different k's. This is important because this is what we want. We want to see how these relative fluctuations go on different scales. Scales of galaxies, scales of clusters, scales of superclusters, scales of small galaxies. You want to see the spectrum, how the different things we see. What's their power? When did they start? What's the initial condition? Okay? Okay, so so 2 things determine these initial conditions. The very initial conditions and the scale that we put from the radiation era, which we'll get to. Okay? So you can also expand if you have a potential. You can also, a gravitational potential, say a Newtonian for now potential. You can also expand it in Fourier modes. And because of our IKR, E lambda squared to the E of IK, to the power IKR things, we get a k squared. And therefore the spectrum must be to the 4. Now, formally speaking, this is because of the uniqueness of the Fourier transform. There's only one way that you can expand the function in a Fourier transform. We did it heuristically by just doing this thing, you know, but there is formal difference. And of course the function needs to be, if I recall well, square integrable and things like that. There are some conditions, but we don't care that much here because it turns out to be a fairly simple field, at least we think it is, that we're describing. Because phases of this field appear to be random. And therefore, the different modes add up like in the central limit theorem. Who knows about the central limit theorem? Bell curve. Okay. So if the modes are random, the different modes will just add up as random numbers when you draw them. Okay? And then you have a central limit theorem. So, and because the field is random, a functional probability of delta of R is a bell curve with a Gaussian probability and an error function defining the area under the curve. Okay? So we think this is the kind of field we have. So therefore, it's completely described by the power spectrum because the phases are random. We don't really need boundary conditions and things like that. Okay? Because the phases are random. We just put a random number generator and get the statistics. So Zohar is asking, we only know statistics? Yes, and that's how we know them. Okay? We know them by, we think it's a Gaussian random field, so we don't need to know the phases, we need to know the power spectrum. Now, we don't know it's completely Gaussian random or not. And there are studies. Are there higher order bispectrum, trispectrum? And there will be, that's another goal of these Euclid and Grace Roman and these big observatories and Vera Rubin and Chile. And these things will be looking. And they looked at, and it's been looked at in the CMB also. But it will be looked at much more in the galaxies. And it's been looked at in the galaxies. The non-Gaussian is quite small, but it's not that highly constrained. So there's still lots of work. And this is a topical subject. It's been topical for 15 years. So is there non-Gaussian? But for the purposes of this meeting, it's Gaussian. For the purpose of our talk. Like there was this joke paper a long time ago, for all practical purposes, meaning writing this paper, we would assume this and that. Okay? So for practical purposes, meaning finishing this talk, we'll assume it's Gaussian. Okay? So what are the heuristics of this? We think that the universe in the beginning, or at least very early on, hard to define the beginning, but very early on, expanded exponentially with a constant Hubble parameter and constant and like we did the solutions last week and so on, this is inflated. Okay? So modes are said to be outside the horizon. This is now going beyond the horizon, so there are no Newtonian here. Okay? You need to take care. Things are going beyond the horizon, you know? Okay, so beyond they're said to go beyond the horizon when their ends, a mode lambda is said to go beyond the horizon when the ends are not communicating, they're not causally connected anymore. So they can be causally connected and then stretched out really fast and lose telephone calls. This happens more or less with the lambda physical wavelength, not the co-moving. By the way, the Ks there are co-moving, I should have mentioned that, but that's not, the co-moving are as of A equals 1 now, and the physical are stretching wavelength. They're stretching the wavelength. When it stretches enough with A, its distance between one end to another of the wavelength becomes larger than the speed light can travel in the expansion than the time. And the distance, light can travel in expansion time, and they lose contact. We can do it more formally in terms of informal terms. That's good enough for us. Then, when inflation is over, so for inflation and things like that, the causal connection and certainly the limit of being inside the Hubble sphere and the Newtonian and so on doesn't work. Because essentially things are expanding inside. And the Newtonian limit works well inside, or reasonably well inside. It works like, as far as people think nowadays, up to like 5 gigaparsec out of 10. That's what we think. So the modes exit the horizon, the Hubble horizon, large wavelength first during inflation. Then when the inflation ends and the expansion is much slower, they re-enter. And I think Alexei will speak more about that, but just briefly because we need it for the power spectrum. So the only scale in this problem really is the time spent of the modes inside the horizon during the radiation era. Now, since our Newtonian description is not valid, we need some form of GR. And things outside the horizon, and GR especially outside the horizon, depend on gauges. Gauge choice of coordinates. These are choices of coordinates, different coordinates. And we'll choose one that makes the Poissons equation that we like so much valid. And this is a gauge that is co-moving with the dark matter perturbation, with the dark matter density perturbation. Okay, so therefore, because it's co-moving with the dark matter density, well, there's only one potential, not two. In GR, there's generally two, one for the time and one for the space. Okay, at least in simple perturbation. Okay, well.
how in GR the evolution depends on the choice of coordinates.
No, because you can have different gauges. You can have different observers. Depends on outside the horizon. Outside. It all works out in the end because your effective Poisson equation is different and the evolution is different. So in one gauge you have different terms in the Poisson equation, and in the other you have different ways for the evolution. So inside the horizon, what is observable is always the same. Okay, outside things in Newtonian conformal gauge, for example, another gauge, things, the density perturbations of the radiation in the radiation air also don't grow outside the horizon. Okay, here in this gauge they grow outside the horizon, but the other thing has an extra term in the Poisson equation for the growth. Okay, so when you do inside the horizon together, they work out the same.
What the principle of relativity law and all the physics laws are.
For observables, it will be the same in the end in all gauges. For observables, okay, one grows, one doesn't grow, but one here has an extra term and so on.
And in principle كان مقتصر بس على اللي هو what's inside the horizon, what's outside the horizon.
You can't measure it, really. You can't, yes, as far as I know, you can't measure it, and that can change by gauge to gauge, yes, as far as I know. There's a little discussion of these things in Bowman's lecture. The ones in triples that he hasn't answered. But as far as I understand, yes, maybe also Alexander Adam can help. But as far as I understand, no. Outside the horizon, they're unobservable, things could be different. But what is observable is the same because your effective gravitational equation or Poisson equation for the potential is different, the growths are different, but it all works out in the end to be the same. You will have here other terms. Whereas our Poisson equation. This thing will not be like we're doing. It will have extra terms. For example, in conformal Newtonian. Okay? Extra terms, but the growth is different outside the horizon. So it's taken care of by the extra terms. So that's the thing. Okay? So it depends on the frame outside the horizon, and it depends on the form of your so-called Poisson equation. Okay, so that's the point. We use here a gauge where the Newtonian equation is there's only one potential because we're co-moving with the perturbation. Okay? We're co-moving with the perturbation, and the Poisson equation is valid, and the important thing for us here is that the growth outside the horizon is possible for the during the radiation year, as opposed to the other gauge, which is the reverse. Okay? Then there'll be extra terms. Anyway, so what are our initial conditions? In these terms, inflation predicts a scalar invariant power spectrum. What does it mean? If you have pure in the potential perturbations, and by the way, this was guessed by people like Harrison and Jankovic until even before inflation, because it's simply a scale-free thing, which was natural because you didn't have any scales to assume you have a scale-free initial conditions for the potential. So these are metric fluctuations, formally speaking. So what does it mean? Again, if we have white noise, this is constant. What is white noise? Poisson noise, meaning you have a bunch of scattered particles and you want to see delta rho over rho angle. One bunch of randomly scattered particles. So this is zero. Meaning that this, which is 1 over wavelength cube, decreases with volume. The fluctuations decreases as big. When I look at larger scales, the fluctuations decrease. Which is expected if you have random noise particles, all frequencies the same, because as far as I go, the larger the larger I go, the larger number of particles I have, and the Poisson fluctuations go as 1 over square root n. So the square goes as 1 over n, which is the volume. the bigger I have, the less fluctuation. It becomes a smooth medium. Okay, many more particles. But this from inflation is not like that. It's like a fractal, self-similar. The larger I go, the more I see the same relative differences. Remember, this was in octaves. Okay? This was the variance per log scale. Okay? So as I change my log scale, I see the same fluctuations, relative fluctuations. Unlike when I change a log scale of random noise of Poisson particles, the fluctuations go down. No, this keeps on generating new fluctuations as I go bigger and bigger in volume. It's like a self-similar fractal. Okay? So because there is a horizon that determines a scale, okay, which I call Higgs here, this horizon Higgs. Okay? So scale invariant fractal density potential perturbations in potential metric. Because they're metric fluctuations in this form, they're also adiabatic, meaning volume compression. They affect all components the same way. Baryons, photons, dark matter, whatever, are affected by these metric perturbations the same way. The modes are random from inflation. They're quantum fluctuations with random modes at exit. And the Gaussian field is defined by a power spectrum. The phases are random, the modes, sorry. The modes are random phases and defined by power spectrum. The current observations support these expectations with the caveats that I said before, the possibility of 3-point correlation functions and bispectrum. By the way, the correlation functions are the Fourier transforms of the power spectrum. If you have bispectrum, you have a 3-point correlation function. In Gaussian, they're trivial, or 0. In non-Gaussian, you can have higher order moments. A statistical distribution that is non-Gaussian is defined by higher and higher order moments, completely by infinite Fourier spectrum. Right, so we take our little, the Poisson equation, we said it valid is a co-moving gauge. Okay? Not valid necessarily in other gauges, but we want to do what we want to do is really to find in the power spectrum, the matter power spectrum is platinum. Okay? Inside the horizon, to compare it physically with the galaxy formation.
Well, I understand this, بس أنا حاسة إنه we didn't put any restrictions over the principle of relativity عشان نقول إنه the physics could be gauge variant outside.
No, it could be gauge, right? It's gauge dependent outside the horizon.
You can do gauge variant.
You can do also outside gauge. Yes, but if it's a gauge, it's dependent on the gauge. Yeah, but yes, you can do gauge invariant Bardeen variables. You can also do that. There's something called Bardeen where you can do it everywhere. Yes. But if you want to fix a gauge, which makes things easier, then it's dependent on the gauge. Okay? Right. So, but you get the same results in the end for observing. Okay, so that's an important point for you. Okay. Yes, and if you can do gauge invariant Bardeen variables everywhere also if you want to do that. Okay. So anyway, for our purposes, we want a gauge where this is valid because it's simple. Like I said, for the purpose of this lecture, we want to, there are people who don't know what the coordinate is and the gauge and things, so so we try to keep it simple because we want to try to compare with observations. Okay? And some of the people who built Euclid also don't know what the gauge is. So, who are going to get Nobel Prizes maybe. Okay? So this is not important for a lot of people. Okay? So I actually started only learning it by talking with people like Adel. Only recently. But you don't really need it for a lot of things. Okay? So anyway, we will assume our co-moving gauge. And the interesting thing about this assumption makes things very simple. Then the matter power spectrum is simply k to the 4 the inflation power spectrum. Immediately you can get the matter power spectrum you see in observations. Immediately, from assuming this thing was constant from inflation, and a fractal thing, and immediately the galaxy power spectrum. And this flattening here. What is this flattening? It's because in our co-moving gauge, the modes that entered, that are small, the wavelengths that are small, and entered the horizon during the radiation era, they don't grow, they have to wait, because the expansion inside is so fast. They have to wait till the radiation era is over. While the large modes, the small k, here, they don't have to wait, because they enter. Okay? These guys wait, these guys don't wait. We get this flattening, and this is a signature of your initial power spectrum. So you move from esoteric thingies to actually measuring the inflationary power spectrum. Okay, you have to be precise also in doing these things, and there are people who, by the way, there was a lot of confusion in the 1990s about it. It wasn't, this is not simple matters, these matters of gauges, they kept people that are really big kept on arguing because there was something that Lifshitz used in the 1940s that was called the synchronous gauge, which had S degrees of freedom. And that was a lot, and people up to 30 years, less, 25 years ago or something, were arguing about it. So it's not simple business. So I'm not trivializing that.
I know, بس ممكن حضرتك ذكرت اسم variables كده.
Bardini.
Yeah, could you write it please بس عشان أبقى
لا, maybe I'll say I don't remember. I don't remember. I got it. So, or Adil, I don't think Adil remembers. Probably I have to say. But you can find them in books like Bowman and so on. And you can, I mean, this is textbook stuff now. It's not, but I don't remember the okay. So Bowman has one, you know what else? A book by Donaldson, Modern Cosmology, Scott Donaldson. What else? Mukhanov, book by Mukhanov. Alexei worked a little bit. Andrew Liddell and David Leith, Inflationary Cosmology and Darkmatter. So there's got a few books you can find in a lot of places. So anyway, for our purposes, this is like the flattening happens like that, right? And this is called the transfer point. What transfers the initial perturbation, k to the 4 in matter, flat flat in the potential perturbations k to the 4 in matter, there's a transfer function between them that measures the time a mode spent in, for our purposes, inside the horizon during the radiation era. And this can be defined as when its wavelength, 1 over k, wavelength is one of the wave number, starts communicating, meaning the conformal time becomes of the order of the wavelength. And then it enters the horizon. So small modes enter first. Yes, small modes enter first, and so they spend a longer time inside the horizon in radiation era. So they are retarded by a conformal time k, which scales, remember, tau squared as the density perturbation. So they are retarded by 1 over k squared, tau equality, which is something fixed. So the t squared entering the transfer function is k to the 4. And that's how we get this break here. Okay? So that's how. This is like k to the 4, and this is, very roughly speaking, 1 over k to the 4. So we expect to see this as a signature. Okay? If we have a scale invariant initial potential perturbation, we expect to see this signature. Okay? K to the 4 on large scales, and flat on smaller scales. The smaller scales that enter the horizon during the radiation. Okay. Okay. So, right. There's another scale much smaller for cold dark matter, and this is called the streaming length of the dark matter. This thing distinguishes things from 100 GeV. Remember the kinetic equilibrium equation? This thing distinguishes things with 100 GeV from things of, let's say, a keV, which move in thermal equilibrium much faster than 100 GeV. Okay? So this is the co-moving distance at a speed v of t that is initially like that, and then it restricts. That defines a streaming length. The particles during the radiation era cannot collapse, as we mentioned, so they stream. And this is, let's say, roughly equivalent to a James length. It makes a minimal size of the structures these particles can form. Okay? It's a minimum size of stuff, the stream. Okay? So the dark matter, we said almost nothing. The cold dark matter, the sizes, it doesn't have a James length, no scale, but it has, other than the scale in the power spectrum, due to the radiation era not growing in density fluctuations, it also has a length scale connected to not growing at all, that is minimal, connected to the streaming, how much is streamed during the radiation era without collapsing. For cold dark matter, this is like the size of the solar system or something. So the smallest clumps of cold dark matter are Earth mass and size of solar system, very small. For things like hot dark matter, neutrinos, this size is huge because they were relativistic actually in the early universe at least, and maybe even now. So this size is huge, and that's why normal neutrinos, even if they have mass, or the main reason why, there are other abundance, but the main reason why you cannot have neutrinos as dark matter, they can't cluster. But well, as you will see tomorrow, there's something called small-scale problems in galaxy formation. And some people think they can be solved by things called warm dark matter. Not the hot dark matter, which is neutrinos, but things in the keV range. Okay? So these are size of dwarf galaxies. They're not one Earth mass, like the cold dark matter, which is 100 GeV. They are a dwarf galaxy of 10 to the 8, 10 to the 9 solar masses, which is because these guys are keV, not 100 GeV. So now this is, for me, this is the important point. The important point is this is the galaxy power spectrum, taken by counting the number of galaxies in the sky. You don't count them very easily. This is really hard technical work. You count the number of galaxies. Here, and you count the fluctuation. And you Fourier, and then you do it in 3 dimensions also. This is projected. And you Fourier transform your delta of R. What you do is you get your galaxy density field, and you write it in terms of the Fourier modes. Okay? And you take the square over the volume you see in the sky, which is usually called the survey volume. The biggest until now are things like Sloan, DES, and so on. It will be much bigger in the next couple of years with Euclid, and huge with things like the Gray Sloan and so on. Okay? So how does this work? We write our dimensionless power spectrum, and we can get the parameters of the universe, like we did with the CMB. We can get from fitting it, from our models, the parameters of the universe. How much variance, how much dark matter, how much dark energy, and so on, from fitting. And we can make sure from this tilting here, we can make sure that the power spectrum is consistent with an inflation and going out, the things going out of horizon, and going in and being trapped in a radiation-dominated area. We see this pattern. So this is evidence for inflation, but there are other models that can produce it. Okay, but they need this horizon exit entry or some other mechanism quite similar. They need it. So this is a test for your initial perturbations, okay? And this is your k to the 4, and this is the flattening. And the more baryons you have, there's something called baryon acoustic oscillations, which is important. They're similar to the sound waves of the CMB, the baryons acoustic oscillation. These are again the sound waves, but they are small here. Why are they small? Because they are made mainly not by baryon photon fluid that was quite strong in the CMB, but by a small fraction of baryon that is 5% the matter and energy content of the universe, and photons which have died down. By the way, Myrna, these are remnants at intermediate redshift of their initial oscillation. You see them at redshift 1 or 2, not at 5. In the galaxy distribution, these are remnants of the initial sound. Here is some I forgot about. Here are remnants of the initial. You see them not at redshift 1000, but at redshift 1 and 2, which is like a few billion years compared to 14. You see them on there. So, and they are small because they're dark matter dominated. This is really another piece of strong evidence for dark matter. If you don't have dark matter, these things should be really huge. And people who don't like modified gravity draw them out without dark matter. And they're completely inconsistent with observation. So you have now 3-4 evidences for dark matter. You have the galaxy rotation curves and the virial theorem. You have the background expansion rate and the supernova. And you have much stronger evidence, in fact, in this and the CMB. These are evidences for dark matter. The rotation curves are actually evidences for modified gravity, modified Newtonian and Einsteinian gravity, MOND. They fit much better than modified rotation. And there's a discussion of the depth between people who like modified gravity and people who like in the observational side more than in the theoretical, and people who like dark matter. The guys in modified gravity can show the rotation curves and something called the mass acceleration relation, and the guys in the dark matter I refuted thus. This cannot be explained other than really contorted ways by modified gravity. Now, okay, so this is the large-scale power spectrum where it's still linear. This is the remnant of the linear regime on scales megaparsec, co-moving, meaning 30 and a quarter light years, million, co-moving, meaning in distances today, where things are still in the linear regime, meaning delta equals delta rho over rho is less than 1. Okay? So this is our recovery of the initial perturbations from inflation. Okay? And this is the parameters we find. And they're consistent also with Big Bang nucleosynthesis narrative, meaning the helium production in the Big Bang. Now, how do you form galaxies from that? This is next time, but I'll give you a preview.
Doctor, have you mentioned what that black line represents?
Which one?
في الجراف اللي في الشمال. في
Zero baryon? Zero baryon.
لا لا لا.
Ah, this is the data! The galaxies.
دي الobservation.
This is the galaxies. Yes. This is the galaxies. So you fit your model with, and you get the same parameters to fit the galaxies as the CMB, as the supernova, and so on. So that's what's really exciting. Except for the but that's exciting too, because you don't know what it is, and it could be a fundamental breakthrough in physics. For all we know, this Hubble tension could be, a revolution in physics. You don't know. And certainly there's no shortage of ideas. The papers have thousands of citations, thousands of references to review papers of ideas. Really a lot of ideas. Yes?
What exactly is modified gravity?
Modified gravity. In the sense I'm talking about, it's called modified Newtonian dynamics. Why Newtonian? Because galaxies are really non-relativistic. In fact, they're so non-relativistic that the correction is in the weak field regime. So you need to modify Newton's law, not only relativistic. But it's difficult usually to get a relativistic version, and it's very complicated. And even when they do very complicated, they find it very hard to find and to fit. Because this needs a cosmological theory, so it needs to be relativistic. Because, you know, you need to do your gauge invariant variance and all that in the modified thing. And this is not easy with these things.
And what's the primary objective of nullified gravity?
To explain the rotation curves of galaxies, things like that I showed in the first talk. Things like that. Instead of this, you don't see any matter in galaxies, but you see rotation going on at large speeds. This is VR. Okay? So it's as if you're seeing like a ball on a string in the dark, and you see a phosphorus ball, but you don't see the string. Given by okay? So I want to, I guess, finish up. So how you form galaxies in the matter-dominated era, the delta grows as T2/3, and when it reaches about 1 in the dimensionless power spectrum, it reaches the nonlinear regime, the fluctuations of the order of the thing itself, and you form a galaxy. In the CDM scenario, you form a dark matter halo. We're not in galaxies yet at all, but these form the seeds of galaxies. So you start with small, and then bigger as delta goes up self-similarly in time during the matter-dominated era. It stops if there is a dark energy after that. But it goes self-similarly. It stops in the radiation-dominated, and it stops in a cosmological constant dominated. But it goes on nicely self-similarly for most of the universe. And some people think this is amazing. Why does it go on until we are born and then it stops? Why? The coincidence problem. Why are we living exactly in the period to make people and then there are no people after that? So here we go. And you form at different scales. I won't go into that. I don't know if I show you a video, but let's leave it next time. Let's leave it to show. This stuff can be simulated, and you can see the structures forming and so on. But I think I'm well beyond time. So. Yeah, I started a bit late now. But I think I'm done. So this is basically how you form the seeds. When these things are large enough, when these things are large enough, they collapse, and they collapse small first. This is important, if I forget mentioning it, because they collapse small first, and this is a huge problem with the James Webb, because you see big galaxies at very high redshift. In this model, the power spectrum is like that. So maybe actually a solution is that the power spectrum things spend more time in the radiation era. Is this worth thinking about? If things spend a lot of time in the radiation era, you don't get very small stuff first. And you don't get very small stuff first at all. And this could solve you the dwarf galaxy problem too. Maybe. There is something, there are models like that, the broken scale invariance. Anyway, this is for another discussion. Okay, so I'll stop here today. This is how you make halos that form, where the gas then starts accreting and forms the galaxy in the sun. The dark matter forms the potential around the gas. So next 2 lectures, we'll discuss how the gas, what's the distribution of these halos, how you can get a mass function for them, what's the distribution function, how they're distributed, how can we know where they are and match them with galaxies, what does the gas do, all the phenomenology of the galaxy formation processes. Like that. So any questions? So okay. Oh yes, of course. You can. I mean, it has astrophysical importance. It doesn't have importance in dynamics. But of course, you can map the dark matter distribution actually instead of doing it like that, which is counting the galaxy. In fact, a method that is becoming more powerful with Euclid is mapping it with gravitational lensing. You can map the dark matter with the gravitational lensing of galaxies. You have a background of quasars or galaxies. There's galaxy, quasar. There's all sorts of things. I'm talking about weak lensing, okay? So, meaning small deviations. And from these deviations, you can do statistics and you find your galaxies a bit elongated and in a systematic way. And from that, people who are really, diligent, they can reconstruct the dark matter density field. Until now, not as good as counting the galaxy, but with Euclid, it will be much better than counting the galaxy. Because it's relativistic also. It depends in gauges where we're not cheating like the conformal gauge or this gauge. It depends on the two potential, phi and psi, time and space. It's relativistic. So you can test modified gravity theory where these are not equal and things like that. So lensing, but these are not the same as the Mond. These are it could test Monds, I assume. But these are more theories for dark energy. There are also modified theories. There are modified gravity theories for dark matter, and there are modified theories for dark energy. Okay? And it can be tested by checking the ratio of these potentials, which is 1, when they exist. I did a trick here to get rid of one. but when they both exist, conformal between the gauge state, they are 1. So this is important.
Both dark energy and dark matter?
Both. Yes, there are theories for dark energy. You can modify GR in 2 ways. For dark energy and for dark matter. There is. I am not aware of electronic Sawa. I'm aware of I worked in unified dark matter Shapligian gases, which is, but these are not really. I don't know if you can you write Shapligian gases. Can you write other Shapligian gases as a modified gravity theory? Maybe you guys don't. I don't think so. Probably not. But you can write it as a scalar field. Yeah, there is something called
You can do anything.
Sorry?
With enough practice, you can do whatever you want.
Maybe, yes. So a Shapligian gas is something that's something I worked on, and it's not liked by everybody. I sent it to PhysRed, and one referee was really happy and so on. The editor didn't accept that. He sent it to another one. Another one wasn't happy, and I made a big fuss, and they sent to a third one, which was happy. So one guy was just saying this as the end of Lambda CDM is God.